Something unusual is unfolding above Earth tonight, and it's happening quietly, almost deliberately out of the spotlight. For the first time ever, an interstellar comet has been placed under a United Nations planetary defense exercise. This level of coordination is normally reserved for objects with uncertain trajectories or potential impact risks, not for visitors that space agencies publicly describe as harmless. Yet here we are, watching exactly that scenario play out around one object, 3I, Atlas. The UN's International Asteroid Warning Network has initiated a coordinated observation campaign spanning from late November 2025 through the end of January 2026. Telescopes across every continent are involved. Space-based observatories have been redirected. Even instruments orbiting Mars are contributing data. On paper, officials describe this as routine training. But the scope tells a different story. This is not a casual drill. This is a full-scale global mobilization. Almost immediately after the exercise was announced, astronomers and amateur observers noticed something didn't line up. If Atlas is behaving normally, why activate emergency coordination servers, joint data relays, and high-cadence tracking protocols? Why synchronize assets designed for worst-case uncertainty? No agency has given a direct answer. But the timing suggests that Atlas has begun displaying behavior that no longer fits neatly into standard models. Over the past week, images have arrived from observatories and backyard telescopes scattered across the globe, and each one adds another layer to the puzzle. Spain was among the first. A long-exposure image revealed a coma that was almost unnervingly stable. Despite background star streaks, the inner core remained tight, circular, and sharply defined. Fragmenting comets don't behave this way. Uneven outgassing distorts the brightness peak. Atlas showed none of that. The energy distribution looked almost mathematically clean. Then came data from Thailand. Conditions were far from ideal, with heavy cloud cover and low transparency. Yet when the image was processed, the brightness profile closely matched Spain's results. Even more intriguing, enhancements revealed a central glow surrounded by layered halos, almost like shells stacked around the nucleus. Comets can produce halos, but symmetry like this requires unusually stable and consistent emission. Hours later, Norway added another piece. From a relatively light-polluted sky and a short exposure window, the tail emerged with surprising clarity. Along its outer edge was a faint curl, a subtle spiral that suggested the material wasn't simply streaming outward. It looked guided, as if rotation or internal structure was shaping the flow. Rotation alone doesn't usually create tails this organized. The pattern hinted at something more controlled. That's when a pattern became impossible to ignore. Spain showed a perfectly stable core. Thailand showed symmetrical halos. Norway showed a structured, curling tail. Different instruments, different skies, same underlying behavior. A stable center. A rotating or guided emission. A halo expanding faster than predictions. Then the Virginia Wide Field image appeared, and it changed the conversation. It captured a faint but extended tail stretching far beyond what earlier exposures had shown. Long, narrow, and remarkably coherent, the tail maintained its structure even in low-sensitivity regions of the frame. This wasn't a chaotic plume dispersing into space. It was a defined stream. With every new image, one thing stayed constant. The core remained circular. Perfectly symmetric. In comets with asymmetric activity, symmetry is the first thing to break. Here, it seemed to be strengthening. This was the moment some astronomers quietly acknowledged that Atlas was no longer matching natural expectations as cleanly as they'd hoped. Almost simultaneously, the UN exercise went live. Inside observatories, schedules were rewritten overnight. Deep sky surveys paused. Telescopes pivoted to high-frequency astrometry, trying to lock onto the comet's true center through its bright coma. That's already difficult with any active comet. Atlas makes it harder. Its jets appear stable across long exposures, barely shifting position over days. Same angle. Same intensity. Same orientation. That alone is deeply unusual. Interstellar comets should be more chaotic than solar system ones. Their volatile content is unfamiliar. Their thermal response unpredictable. Their rotation often erratic. Atlas, by contrast, seems restrained, almost disciplined, as if something internal is limiting its motion or anchoring its activity. And that's where the mystery. As infrared data came in, the picture grew even stranger. Atlas shows an unusually high carbon dioxide ratio in its coma, significantly higher than what's typical for long-period comets. This points to a formation environment very different from our solar system, possibly colder, chemically skewed, or shaped by conditions we haven't directly observed before. On its own, that wouldn't be alarming. Interstellar objects are expected to be exotic. But chemistry alone doesn't explain the consistency of Atlas's behavior. The jets don't fan out. They don't swing dramatically with rotation. They don't wander. They hold their direction. Some scientists suggested the comet might be rotating extremely slowly. Others proposed vents locked into fixed orientations. Quietly, many admitted neither explanation fully fits the data. The stability is too persistent. At the same time, amateur observers began noticing subtle brightness pulses. These weren't dramatic flares, just small, rapid increases that didn't appear in NASA's smooth light curves. When amateurs compared observations, a pattern emerged. The comet brightens slightly. Then the outer halo expands. Then the tail sharpens. Through it all, the core remains unchanged. It behaves less like a chaotic body-shedding material and more like a stable engine surrounded by volatile vapor. That description makes some scientists uncomfortable, not because it implies anything artificial, but because it challenges how cometary activity is supposed to work. Astrometric data added further tension. Atlas shows tiny but persistent deviations from purely gravitational motion. They're not large. They're not dangerous. But they're consistent. And they don't perfectly match the expected profile of outgassing-driven acceleration. This kind of complexity is exactly what planetary defense exercises are designed to test. Objects that aren't threatening, but aren't fully understood either. Publicly, agencies remain calm. The Asteroid Warning Network denies any emergency. NASA states that everything is within expectations. The European Space Agency echoes the same message. Yet behind the scenes, coordination channels are active around the clock. Tracking assets near Mars are involved. Some observatories received private notices. Global observation density has tripled. Data servers are running at full capacity. Officials say this is just practice. Maybe it is. But humanity has never before placed an interstellar comet under a months-long, structured planetary defense campaign. Not one passing at a safe distance. Not one officially labeled harmless. And not one whose behavior grows more unusual with each night of observation. The simplest explanation may be the correct one. Atlas could be entirely natural, just an interstellar visitor with unfamiliar chemistry and structure. If so, this is a rare and valuable opportunity to stress test our planetary defense systems on something exotic and unpredictable without any real danger involved. But another possibility lingers quietly in the background. That there are still features not fully understood. That anomalies need confirmation before conclusions are drawn. That the extraordinary symmetry, stable jets, chemical signatures, and slight accelerations demand a level of precision humanity has never practiced on an object like this before. Whatever the truth turns out to be, one thing is undeniable. 3I, Atlas is now the most closely watched interstellar object in human history. Not because it threatens Earth, but because it challenges assumptions. It pushes our detection networks, our models, and our confidence in what we think a comet should be. Over the coming weeks, as the UN exercise intensifies and data continues to pour in, the mystery will either sharpen or slowly dissolve into clearer science. Either outcome matters. Objects like this don't visit often. And when they do, they tend to change what we think we know about the universe we're moving through. ChatGPT can make mistakes. Check